I hope everybody's cool with it being recorded. Please, somebody tell me if they're not. Let's see here. That's great. Okay, so welcome. Oh, by the way, it's probably a good idea to stay on mute just if you're not saying anything because, you know, background noises and whatnot. However, Math Club, this is very informal. This is for you guys. So anybody, just type in with a question, especially if I'm in the board and can't see the chat very well. Just let me know if any questions pop up. Welcome to the first Math Club. We're still virtual for at least a little while. I can't wait for us to all get back together in person, but we will keep persevering in the meantime. What I want to talk about is something that's kind of an old chestnut, Euclidean algorithm. And fundamental theorem. So I'm going to start off with something that's probably borderline embarrassing for me to do in a math club. And that is, so let's take a number and another number. Now, we can divide. Grade school, we could have divided this. This has got to go in 9 times, right? That was 18. Wow, that's pretty serious. 6. Looks like it goes in 9 times again. Now it's down to 15. Yeah, that's right. And finally 152. And yeah. I can't believe this.
And you do think some people here.
I should put an example if you put in, so this has remainder 0, but of course, if we had divided 19 into 3, 7, 9, 6, 1, then this would have been 1997 with remainder 18. One of the things that we knew about the division algorithm is when we divide a number, an integer by another integer that's not 0, you can always get a remainder that is no more than what you divided by. And you can expand this to something more general. You can expand this to negative numbers by instead of just taking the remainder, take the absolute value. So let me formally tell you what the Euclidean algorithm is. So I said you didn't really need any background for this, and you kind of don't. But let me tell you what this is anyway. And if you don't like thinking about it this way, just think about the integers or polynomials. R is an integral domain. What I mean by this is just basically a structure where we can add and multiply, right? The integers is an example of one. You also need to have negatives, but the integers is one, the rational numbers, the real numbers, polynomials over the reals. If you add 2 polynomials, you get a polynomial over real. If you multiply 2 polynomials, you get one. But if you don't like thinking about it, and integral domain also means that it has no non-zero zero values. So what this means is the equation AB equals 0 implies A equals 0 or B equals 0. So you can't have 2 non-zero things multiplying together to give you 0. And if you think that that's never possible, well, just think about matrices. It can certainly happen there. So well, I'll put it this way, R is the Euclidean domain. if there is a function phi from the non-zero elements, so here you might think the non-zero integers, into the natural numbers. Now, the natural numbers union zero, this can actually, this can be any well-ordered set, if you like that sort of thing. But there's a way to associate to every non-zero a natural number of zero, such that property zero, phi of AB is less than or equal to phi of AB for all AB in the domain. And I'll write property zero because actually I'm going to talk a little later where we need this. Now, here's the big. Given y and x in R with x not zero. So if I take two elements of the structure, two integers, and x is not zero, I can divide x into y and get a remainder. Well, of course, I can always do that, but there's something special about this remainder. With Q, R, elements of R, and R is zero, or phi of R is less than phi of X. Okay. So what this function is, sometimes it's called a Euclidean function or a Euclidean norm. And what this means is, in a certain sense, you might think of this as measuring the size of whatever you put in here, the size of A or the size of R. Because its output is going to be a number, a non-negative number from zero on up. And here's the importance about size. Taking two elements, you can divide y by a non-zero element, and you can get a remainder whose size is strictly smaller than what you divided by. Or the remainder is zero. So you get dividing them there evenly. So there is a Euclidean function on the integers. So here's an example. Anybody want to guess what this one is?
X.
You're close. You're close. Got to adjust a little bit because remember.
Oh, the absolute value. Yeah.
There you go. That'll work. So basically, what this says is you can divide any number, any integer, by another integer, and your remainder is no bigger than the absolute value of what you divided by, right? Because of course the negatives, the smaller they get, the larger an absolute value they get. So you got to straighten that out. Here is another example. This is a set of polynomials with real coefficients. This is another example of something that's got a Euclidean function on it. This is an old familiar one. I mean, actually, when you first played around in calculus or analytic geometry, you looked at a lot of polynomials, right? You took their derivatives and integrated them and so forth. Well, polynomials are one of these integral domains. If you multiply two polynomials and you get zero, one of them had to be zero, and it's closed under addition, subtraction, and multiplication, right? Anybody know what the Euclidean function is here? So let's suppose p of x say a typical polynomial. Let's suppose this polynomial is not zero, so at least one of these coefficients is. And in fact, what we'll do is we'll say that an is not zero. So we'll say that this largest term is not zero, because if it was zero, I would just end it at n minus 1. All right. I know what the Euclidean function here is.
The degree of the polynomial.
Let me see if I can give you a kind of a quick look at how this works. And, you know, I guess if I was doing a proofs course here, I would do this more generally. But I'm just going to do this with examples, right? So, ln x, and I'm going to make it Monty just to make it easier, but it doesn't matter. Or not, x is a choice here. I'll call it C. And actually, I guess what I'm going to do is I'm going to do this. Now, I want to divide y by z. And this is obnoxious. I put the 2 in front of there to demonstrate something later. If I wanted to be lazy, I would have just made that a 1 coefficient, and you'll see why in a moment. Let's divide this into x to the 5th and we'll see what degree plays a role. How many times does 2x cubed go into x to the 5th? I need a 1/2 there. 1/2 that is x squared. And so that's going to give me an x to the 5th. Then I'm going to have a 1/2 x cubed. And then I'm going to have a 3/2 x squared. So I'm doing this just like I would have done division when I was in grade school. Subtract, that gives you a 0. This is all 0. This gives you minus 1/2 x cubed plus 3/2 x squared plus 2x plus 5. Okay. And let's see, 2x cubed goes in here one more time. I guess I can make this a minus 1/4 by multiplying this by, I'm sorry, to make this minus 1/2, I multiply this by minus 1/4. And so that's going to get minus 1/2 x cubed minus 1/4 x minus 3/4. And if I subtract again, that's dead. Then I get an x squared, so I'm going to get 3/2 x squared. When I subtract this, I'm going to get 8/4, so 9/4 x, and I'm going to get 23/4 here. Now, how many times does x cubed, 2x cubed, go into 3/2 x squared? Well, it doesn't, because you can't use a polynomial anymore. You need an x to the minus 1 power to max this up, right? So I'm stuck, I'm finished. And so what this means, and you can actually take this apart and check this. When I've done this division, assuming that I did this right, this means that my polynomial that I started with, that I divided into, x to the 5 plus 3x squared plus 2x plus 5 is equal to, my quotient here is 1/2 x squared minus 1/4. That's what I divided by. Plus this remainder. And there you go. So this is a specific example, but I hope you all kind of get the gist of this, that this kind of always works. And the reason it always works, and this is the reason I put the 2 here, is basically I can adjust the 2 by dividing by anything I want to make it match right here, right? If I allow my coefficients not to come out of the real number, well, they could have come out of the rational number, but if they only came out of the integers, I couldn't do this anymore. I get stuck along the way. So this is another example of a Euclidean domain. That is polynomials over the reals, or in fact, you can generalize this to over any field in one variable. And the degree is the Euclidean function. I'll give you one more example that you can go home and think about this one. Let's let R be. Let's let R be power series over the variable x. Well, what I mean by power series, this is not Calc 2. Don't worry about plugging anything into it. These are just sort of infinite polynomials. They're symbols. We can multiply them, we can add them. And in fact, if you multiply 2 power series like this, you get 0. One of them has to be 0, so it's an integral domain. Now, of course, any polynomial is a power series because at some point the coefficients could all become 0, right? But not every power series is a polynomial because I could fill this all up with 1s and 2s, whatever I like. So this is a typical element. Let me change this to say a typical non-zero element, because that's where I want to put it. What do I do about this? Because unlike polynomials, there is no degree in general, right? I mean, polynomials, we looked at the degree, we looked at how big it was, what was the highest term. What do we do here? Let me help you out a little bit. Suppose AN is smallest non-zero entry. I mean, it could be A0, but we'll just say AN is the smallest one. I know that there is some non-zero entry because we're assuming this is non-zero, right? So let's suppose it's the smallest one. Can't we rewrite the power series as x to the n times AN plus AN plus 1x plus AN plus 2x squared, etc. And I'm going to let phi of this be n. So instead of going the highest, I want the lowest. This is often called the order. And this is actually, this actually makes the reals, power series over the reals also a Euclidean domain. Okay, so let me give you another example. And these come all over the place. I'm going to generalize this, but I want to start with a very famous one. This is the famous Gaussian integers. This is just like the complex numbers, except now I'm assuming that A and B are both integers. They can't be just anything, they just have to be both integers. When you multiply anything, two things in here, it's still there, and when you add them, they're still in there. Consider phi from r minus 0 to natural numbers. Actually, the natural numbers, also the natural numbers 0 by phi of a plus bi is a plus bi times its conjugate, which is a squared plus b squared. Notice the input is a Gaussian integer, the output is the sum of two squares. So it's certainly into the natural numbers. This is called the norm, and this generalizes to other rings like this. Let me point out something about this norm here. And that is, notice that phi of a plus bi times c plus di is a plus bi c plus di times its conjugate. Which is, if I rearrange this, a plus bi, a minus bi, c plus di, c minus di, which is a squared plus b squared times c squared plus d squared, which is the norm of the first times the norm of the second. That is going to prove useful. Now, one of the things about this is actually a Euclidean norm. This thing also has this division algorithm, just like the integers, just like the power series and polynomial that we just looked at. Let me show you why this works. So let y equal c plus di and x equal a plus bi. So I'm going to try to divide y by x, and I'm going to show that I can get this thing to come out with an appropriate smaller remainder. So if you look at y over x, this is c plus di over a plus b. Now, one of the things that I can do, and this takes me back, this reminds me of being in like high school, when they would tell you to do things like, find the conjugate, rationalize the denominator, and things of this nature, right? That you were quite convinced somebody was just doing this to make you angry. Well, let's do this. A minus bi. A minus bi. And let's see what we get. Well, I'm not going to beat this dead horse, but I get a denominator that is an integer. And I get a numerator that is AC plus BD plus I times AD minus BC. And so basically, this is a rational number plus a rational number times I. So I'm going to write this as Q1 plus Q2I. Everybody agree with that? Now that quotient, if this had been perfect division, that quotient would end up back down at ZI. Maybe it did, maybe it didn't. It depends on whether this thing divides this and this or not. Maybe it does, maybe it doesn't. But I do know that it ended up rational number plus rational number times I. And so what I'm going to do is choose M, N, and Z as close to Q1, Q2 respectively as possible. So basically what I'm doing is I'm picking m and n to be the closest integers to these rational numbers that I can get. If they are integers, then I'll pick it exactly. But let me point out that the absolute value of n minus Q1 and the absolute value of n minus Q2 are both less than or equal to 1/2. All right, that's the worst I can miss. That's as bad as I can do. Right. So let's note that C plus DI minus A plus BI times M plus NI is equal to R1 plus R2I. I'm not saying much of anything here. These are all integers here. And so what I'm going to get, I'm going to get a big mess. But when I sort it all out, my real coordinate is going to be an integer and my imaginary coordinate is going to be an integer. That's all that's going on there. But let's try to measure this. The norm, and by the way, this should look familiar because if I put this on the other side of the equation, this should be C plus DI is A plus BI times this plus this. This is my quotient. This is what I divided by, and this is going to be my remainder. If you look at the norm of R1 plus R2I, this is the norm of A plus BI times Q1 minus Q2I minus M plus Ni. Which is right, because basically the C plus DI is actually equal to A plus BI times, this is actually A plus BI times Q1 plus Q2I. So this is the norm of A plus BI times this mess here. Well, remember the Q1 minus M plus I times, actually I'm going to write Q1 plus Q2 here, I guess. Q2 minus M. And notice that the norm of the product of two things is the product of norms. Here I'm writing N for phi, because that's an old habit of mine. But phi of the product of these two things is phi of the first plus phi of the second. So this is norm A plus BI times the norm of this thing, Q1 minus M plus I, Q2 minus M, which is norm A plus BI times QI minus M squared plus Q2 minus M squared. right? And this is less than or equal to, that right there is 1/4, it's a half squared, it's less than or equal to 1/2 squared and 1/2 squared. That's 1/2, which is strictly less, because that's not 0, it's strictly less than 1 plus pi. So this is also Euclidean, because my remainder, the norm of my remainder is smaller than the norm of what I divide. Okay, any questions? So what we have so far is an example or 4 examples of Euclidean domains. Now here's there's another thing I promised to talk about, and that was the so-called fundamental theorem of arithmetic. And basically, this is something that's an old familiar friend in the days of the integers. It says any natural number bigger than 2, or bigger than or equal to 2, can be factored uniquely into primes. This also goes for the negatives, because if you ignore signs, you have any integer, like say 12. 12 is -2 times 3 times 3. We ignore the plus and minus 1, because I could do it this way: 2 times -3 is 3, or -2 -3 -3. And so I don't really make a distinction of whether it's a minus or not. 1 and -1 are different when you talk about factorization, because they're both invertible. So when it comes to factorization, they don't really bring anything to the proceedings. Let me give you a couple of definitions. Some of this you may have heard before. Definition. Let R be a domain. Again, think the integers if you like. Pi in R is irreducible if its only factors are itself and, well, for the integers, I'm used to saying the only factors are itself and 1, but I really should say its only factors are itself plus or minus 1, or minus itself. The more general statement, units. Okay. So in other words, what this means is pi equals AB implies A or B is a unit. So the translation of the integers, if you can factor something, one of the two factors has to be 1 or -1. And to say it's a unit is a more general statement. A unit in the more general situation is just something that divides 1. Like in the integers, for example, 2 does not divide in 1, only 1 and -1 do. But in the Gaussian integers, there are more units, because if you look, I divides 1, because I times I cubed is 1, and I cubed is another element. In fact, in the Gaussian integers, you got 4 units: 1, -1, I, and -I. And those are the only ones. We're going to forget about that. Let me add to this definition. Pi is prime if pi divides AB implies, well, let me also say pi is not a unit. I should have also said that irreducible. I'm going to assume that irreducibles themselves are not units. A unit, and pi divides AB implies pi divides A, or pi divides. Now, as it turns out, and you might try to prove this for yourself, if that kind of thing excites you, it turns out that any prime that is not 0 must be irreducible. Actually, maybe I will show you that really quick. If you have a prime And suppose pi. Now, of course, what I need to show is one of these two is a unit that is divided 1. Well, without loss of generality, pi divides a, because it divides its product. So a equals k pi. And so let's go back to this equation. We get pi is k pi b. Cancel the pi, and you get 1 is kb. That means that b is a unit. Because b divides 1. Right? Now, I played it fast and loose here because the reason I can cancel that pi is because I've got an integral domain, right? So the product of two things being 0 means that one of the two things is 0. The converse is not true. Irreducibles do not have to be prime. In the integers, they are. And in fact, in any mathematical structure, any integral domain that actually has the fundamental theorem of arithmetic, then these two are the same for non-zero elements. That is to say, any non-zero prime is irreducible and any irreducible is prime. But not everything is that way. So let me give you a couple of examples. This is just like our Gaussian integers thing, only it's a little bit more exotic. These are complex numbers that look like a plus b times the square root of -5. It turns out in this range, 6 is 2 times 3. No shocker there. Notice, and it turns out these are irreducible. It takes a little bit to show that. You need to know something about the norm of this. The norm of this is not a Euclidean norm, but it does serve some other important purposes. But notice, if you believe this, notice the 2 divides this product, but doesn't divide either one. It's irreducible. An example that's easier to see. Look at all polynomials. They can be anything you want, the coefficients and the reals, except there's no linear term. The coefficient of the linear term is 0. Notice that x squared and x cubed are irreducible. Because after all, how can you break them down? This is degree 2. To break this down non-trivially, you need degree 1, and it's not there. And this has the same problem. If you notice, x to the 6 can be written as x squared, x squared, x squared, and it's also x cubed, x cubed. Notice, x squared divides this product, but doesn't divide either one of them because there's no x. X cubed divides this triple product, doesn't divide anything. So these are good examples of irreducible elements that are not prime. Now, let me give you another kind of cool, this is a cool spin-off. This is a cool spin-off of what it means to be prime. Note, if an element has a prime factorization, then it is unique. So when you hear the fundamental theorem of arithmetic and it says, well, okay, anything can be written as a product of primes uniquely, the uniquely part, that's redundant. Because whenever you can write everything as a product of primes, it's always unique. Now, if you say it's got an irreducible factorization, now you need to add the you add the extra qualifier that it's unique. Why is this true? Well, let PI be primes and pi I irreducibles. In fact, I'm proving something a little bit more general than what I stated, and that is not just that these factorizations are prime, but they are that actually any irreducible has to. This also has to be a prime factorization. So I've got primes here and primes here. Let me give you a really, really sloppy proof very quickly. P1 is prime, and it divides to the right side of the equation, right? What does it mean to be prime? It means it divides the product of two, and more generally in things, it has to divide one of them. So P1 divides pi1 without loss of generality, because it has to divide one of these. But pi1 is irreducible, which means that these two are essentially the same up to a unit, right? So you cancel. And now you keep tunneling down. And by induction, you can show that you actually have to have the same number and you exhaust everything. And so your original factorization, the P's, that was it. Okay. So that's real fast and loose, but that's basically the gist of it. Okay. Any questions? Let me give you a theorem. So I promised to tie these together. Euclidean domains and the unique factorization theorem. How did I state this? What are the Euclidean domain? So this is any domain where you have one of these Euclidean algorithm things, right? Any two non-zero elements of R have a greatest common divisor that is a linear combination of them both. Any two, we'll say non-zero, you can generalize this a little bit, elements have a greatest common divisor. Actually, you don't even really, the greatest common divisor myself here. That is a linear combination. So if I walk up to you on the street and give you two elements, X and Y, not only do X and Y have the greatest common divisor, but you could write that greatest common divisor as a linear combination of X and Y. So to this end, let's go through this real quick. Suppose X and Y are non-zero, and let's let call this L equal the set of AX plus BY. So what am I doing? I'm collecting all possible linear combinations of X, Y, and I'm putting them together in a big set that I call L. And then I'm going to let D be the set of P of Z, C in L not zero. So what I want to do now is I'm taking all possible linear combinations. Some of them are zero, right? It's like they gave me zero. I don't care about those since X and Y are both non-zero. This has stuff other than zero. I am going to collect every non-zero element and I'm going to use my Euclidean function to measure it. Because remember, I think of Euclidean things is that they sort of measure the size of it. So I'm going to take this, and this is a subset of the natural numbers, well, union zero, which is not empty. And it's not empty because, well, because D itself is, D has elements in there that are not zero. let C be an element of L. So Z is AX plus BY, such that B of Z is minimum. I know that D has a smallest element because it's a set of natural numbers union 0. And I will pick the smallest element out. And there's some Z that has that smallest measurement. It's more than likely it's not unique, but there's at least one of them, and I'll pick that out. So I claim that Z divides X. Let X be Q's equals R. Note that R equals X minus QZ, which is X minus Q times AX plus BY, because Z is a linear combination. And so this is an L, right? Because R is a linear combination of X and Y. And so, phi of R cannot be less than phi of Z, because phi of Z was chosen to be minimum. Therefore, R is 0 and Z divides X. Also, Z divides Y. By the way, because the symmetric proof to this, we've got the Z divides X, it also divides Y. So there you go. We have a linear combination of X and Y that divide divide both X and Y. And if you want to show us the greatest common divisor as well, that's actually pretty easy. So here's a corollary. And then after I'm done with this corollary, I think I'll just got a couple of concluding remarks, as well as showing some quick interesting example. Corollary. In a Euclidean domain, any irreducible and this is actually going to do it, and I'll kind of tie this together kind of a fun way in a moment. Let pi be irreducible. And suppose pi divides AB. So we can write pi k equals AB for k and R. Okay. If pi does not divide A, the GCD of pi A is 1. Somebody tell me why. So how can I make this claim that if pi doesn't divide A, then the greatest common divisor between the two has to be 1? What is it I know about pi? Well, I know that in Euclidean domain they have a greatest common divisor. Greatest common divisor must divide pi. So my choices are basically 1 and pi itself. If pi doesn't divide A, then that's my only choice. Everybody cool with that? So there exists R, S, and R such that R pi plus SA is equal to 1. Now multiply this by B, and R pi B plus SAB equals B. Notice that pi divides this, and pi divides this, because remember, pi divides AB. Therefore, pi divides B. So we've shown pi doesn't divide A, it must divide B, so pi is a prime. Now, that essentially does it for the most part, because what we've got now, this shows that a Euclidean domain, every irreducible is prime. And so really all that's left is to show that every element in a Euclidean domain is actually a product of irreducibles. This can actually be shown. It's easier to show it if I have that property 0 that I never really used. If you do that, there's kind of a short proof to it. You can argue that everything is a product of irreducibles. If you do not use that property 0, it turns out that any Euclidean domain, actually a Euclidean domain may have several different Euclidean algorithms. And it turns out if you have any Euclidean domain, you can tweak the algorithm so that it does have one with property 0, but it's actually kind of surprising. And if you don't go that way, you can actually show it anyway, just by going through some older kind of stand. Or you could go a long way around, and that's really not our scope. So let me give you kind of an example here to close this out. So here are the possibilities. Some possibilities, not all of them. One, Euclidean, and some possibilities for I guess I'll take the time to write this down. So in field Q square root of D, where D is a square for integer, you have these special kind of rings. These are called rings of algebraic integers, and they are in the form D is equivalent to 1 mod 4, Z square root of D, D is equivalent to 3. So for a quick example, the Gaussian integers, D is -1. And for the Gaussian integers, see that's 3 mod 4. If you had something like D is -19, -19 is equivalent to 1 mod 4. It's in this form. These are special rings that have a technical condition called integrally closed, and they're candidates for being Euclidean. Every one of these has a norm. And I'll write a norm instead of phi. A plus B, 1 plus radical D over 2. The norm of this is A squared plus AB plus 1 minus D over 4 times B squared. If D is equivalent to 1 mod 4. And the more familiar norm of A plus B radical D, this one's one like the Gaussian integers is A squared plus D squared. I'm sorry, that would be minus. So with Gaussian integers, D is -1, and you get this. We use the Gaussian integers norm to show the Gaussian integers were equivalent. This works for several others. So here's a list. Norm. And in fact, I will give you the entire list of them. For D negative, they correspond to D equals -1, -2, -3, -7, -2. for those values and only those values for B, this thing is Euclidean with the norm being Euclidean. And actually, these are the only Euclidean ones, period. For D bigger than 0, and these are just quadratic, the list is a little bit longer, but still pretty short. 2, 3, 5, 6, 7, 11, 13, 17. 19, 21, 29. 33, I think. Yeah, 33, 37. 41. 57, 7. For positive D, the real ones, these are the only ones that are norm Euclidean. That's it in the universe. Number 2, Euclidean. Not Euclidean, not norm. Here's a couple that are verified. Z adjoining with square root of 69. Z adjoining with square root of 14. And in fact, this one was only verified in 2004. This is Euclidean, but not norm Euclidean. If the generalized Riemann hypothesis is true, then actually it turns out that everything that has unique factorization is also Euclidean, maybe not norm Euclidean, but it's also equivalent, or is also Euclidean, but we don't know that until we know whether the generalized Riemann hypothesis is true. But that's probably why we don't have any counterexamples of that. Number 3, fundamental theorem of arithmetic, but not Euclidean. And I will give you well, let me do it this way. Here's the ones that have fundamental theorem of arithmetic. -1, -2 from the negative D's, -1, -2, -3, -7, -11, -19. There's just a couple more, 43, 67. Actually, that is an exhaustive list of all the negative D's. And these are the only ones that are Euclidean. And these are, oops, I'm sorry, stuff at 11. And these are not Euclidean. And that's known. These are all Euclidean, the norm Euclidean. These all have the fundamental theorem of arithmetic. But for everything other than this imaginary quadratic case, if you believe the generalized Riemann hypothesis is one, it's all, they should all be the same. Only nobody really knows. Now, in general, Euclidean domains do not have to be, or I'm sorry, fundamental theorem of arithmetic doesn't have to be Euclidean. So, for example, if you look at this ring, polynomials of 2 variables, that has a fundamental theorem of arithmetic, but it's not Euclidean. Okay, that's enough. Any questions? Questions on that?
So there's this finite list of D's where you get, for example, like a norm Euclidean ring in this
Right.
Z adjoin root, or Z adjoin 1 plus root D over 2.
Uh-huh.
But what's the reasoning behind this list? This is very bizarre to me.
Oh, well, so.
Because not all of them are primes, so.
I know it is kind of strange. All of these are prime, but not the real case, right? The real case, I think you can have up to probably 2 primes or possible. The real case, actually, one of the things that's different between the imaginary case and the real case is the imaginary case always has only the units plus or minus 1, except in 2 cases. The Gaussian integers has 4 units, and the case for -3 has 6 units. It has the cube roots of unity. But once you go beyond that, there's very few units. The real case, on the other hand, all of those have infinitely many units. And that actually changes the nature of the game a little bit. But yeah, so what tends to happen is, if you like such things, for the imaginary case, as you get a bigger and bigger negative number under the radical, the class number tends to go up. And I think there's a result that says something like, for any given possible class number, once you get beyond a certain point, it's always bigger than that. And so these things are kind of ill-behaved. It is not known for certain whether there are infinitely many of the real ones that are UFDs or not. Most people would say definitely that is probably true, but I don't think there's proof yet. Right? And if you believe the generalized Riemann hypothesis, everyone you find is a UFD is also a Euclidean. But these are 2 examples of ones that are UFDs that are only recently, this one only recently shown was actually Euclidean. But I mean, I think that people that believe in the Riemann hypothesis probably believe that's true. So, okay. Other questions?
I guess I have another one. So the Euclidean function on the Gaussian integers is right, the square of the complex absolute value, right? So if you look at just the subset of just the real integers, then the Euclidean function is like the square of the usual one on the integers. And is that always the case, that if you have a Euclidean domain and you square the Euclidean function, you get another Euclidean function for the ring?
It occurs to me that that sometimes might be too big. You might have to scale it back down. But I'm not really sure about that. But you are correct in the sense that you know, if you have a Euclidean function, there are ways to scale it. So usually, if you've got a Euclidean function, you have several of them. I don't really know what's out there about ones that are actually sort of qualitatively different, you know, if you know what I mean. But one of the things that I can remember puzzling about this when I was in grad school, I was like reading some stuff. I was like, you know, if I have a Euclidean function, or if I have a Euclidean domain, and I'm clever enough, I can probably figure out what the function is, right? And I can figure out whether it's Euclidean or not. But on the other hand, if it's not Euclidean, how in the world do you show that there's never any such function? Right? I mean, how do you know out there in the depths of some Stephen King novel, there's some crazy function that makes this work? Well, one of the things is there is a consequence of having a Euclidean algorithm. If any domain that has a Euclidean algorithm has these things called universal side divisors. And so Euclidean implies it has these. If you can show that the ring doesn't have these kinds of elements, then it can't have, it's not an if and only if, right? So Euclidean implies that you have this, right? And so one of the techniques, like to show, for example, that the case for -19, which is the smallest example that I know of something that actually has unique factorization, but is not Euclidean, the standard thing to do is to show it doesn't have these universal side divisors. You know, it is kind of interesting. So how many of you out there have ever had an algebra course where you've seen the proof that Euclidean implies PID, and then you've seen maybe that a PID implies the UFD? You see it? And those of you that are in my algebra class now, I feel sorry for you because you're going to see it. But This is interesting because the proof that Euclidean actually has a PID, which is not something I talked about, is pretty easy. The proof that a PID is a UFD, there's many ways to do it. All of them that I know of involve the action of choice. And I actually looked this up, looked up a paper. There was a paper actually written in 1976, I think it was, some logic thing. It was, I don't really know the journal, but I looked up the paper. And anyway, apparently you cannot prove that a PID implies a UFD in ZF. You need choice for it. And in fact, you also can't prove that a PID has a maximal ideal without the action of choice, which really is kind of strange to me, but that's the way the cookie crumbles. Okay, others? All right. Thanks for coming out today, y'all. I hope I didn't keep you too long. I hope y'all have a great weekend. Stay tuned for the math club next week. I'm not sure who the speaker is again. I hope for your sakes it's not me. And don't forget to give the problem of the week a try. That ought to be fun for you. All right. All right. You all take it easy, and we will see you next week.
Thanks, Jim.
Jim.
See you then.
Sure
Thank you.
thing. See y'all.